to speak about the 14th Hilbert problem, and let me first formulate the result, the question. Okay, the 14th Hilbert problem is as follows. In the modern terms, for which groups G in G and K, the invariant algebra B, where B denotes the polynomial ring with respect to G, is finitely generated.
Oh, this seminar is is finitely generated.
Finitely generated.
Am I right that the Hilbert problem was whether this is true always?
Yes, let me comment it about a bit.
I'm sorry, another important remark. I would prefer in English not to say invariant algebra, because invariant algebra, this is algebra which is invariant, which is stable under G action. And you mean the difference, you mean algebra of invariance, consisting of elements which are invariant.
It was my first attempt, and then I changed to invariant algebra because I read at some place.
I know that people use different variants, but mathematically it's better to say the algebra of invariance.
Okay, so in fact, in the list of Hilbert's problem, which was published after the International Congress, there was another formulation, because when it was written and during the international conference in this year, it was assumed that this problem is solved, that for any G inside GLM, the algebra of invariance is finitely generated. But later in the proof of Maurer, there was found a mistake. And the Congress formulation was as follows. Let we have some field K that is between our ground field and rational functions. Is it true that its intersection with the polynomial ring is finitely generated? If we will take K equal to the rational invariant functions, then we will obtain the first formulation, and it was assumed that this is always true, so the question was whether the second one is true. But then the mistake was found, and from that time there was a question whether it holds for all groups G or not, whether there are some groups such that this algebra of invariance is not finitely generated. And there were many positive results.
I'm sorry again, but short introduction. Again, as far as I remember the history, during this Congress, Hilbert gave a talk. And in this talk, he formulated something like 10 problems.
Yes.
And this problem was not among them.
Yes, it was published after the
And then he wrote some text with a list of problems, and he enlarged the list of problems up to 26 or something like that.
23.
23. And this appeared in this list.
The talk of Congress was too short, and there were only 10 problems.
But I understand that we will discuss this first question, but is there something interesting in the second statement which is not in the first. So is something interesting, some fields K which are not fields of invariance and so on?
Sometimes people construct such fields K, not like fields of invariance, but I don't know some example.
As far as I remember, the solution is as follows. So the problem for group was assumed to be solved, that it's always finitely generated. And Hilbert asked whether the following generalization of this question holds. Okay? And then, again, I'm not sure, but it seems that the counterexample to this more general question was constructed earlier. And then it was constructed a counterexample with a group of invariants.
My question is that now we are investigating some invariants, but are there works about fields which are not invariant?
Yes, there are.
Yes.
So there were counterexamples to this more general question.
Some modern
Without invariants.
question,
Yes.
some modern
Modern I don't know, but
investigations.
in 50s.
Yes, but we will think about the first variant of this problem. So some positive results were before the concretes. For example, Gordon in this year proved that the ring of invariance is finitely generated for SL2. He used so-called symbolic method, but this method doesn't help for SLN, for example. And Hilbert, in his final work in 1890, proved for SLN CZ for G equal to SLN C that the ring of invariance is finitely generated, but in fact he laid a foundation for proofs in much more general cases, and this sketch of proof is very helpful for many other works. Also there were results by Wurwitz, 1897. He proved for orthogonal group and UN. Then Notter.
And G is not an algebraic group.
As far as I have read, we may assume that G is an algebraic group, but I don't know.
No, it's very easy. Take any subgroup in GLM.
Yes.
Take its closure in the Zariski topology.
Mm-hmm.
Then the algebra of invariance doesn't change.
My question is about UN. What is it?
Unity.
It's algebraic.
You might consider this over the real numbers, but in Yulia's setup, you can just take its closure in and use algebra of invariant.
I don't know about the field, so.
Is he G or H?
I'm sure that it is
How to
not.
write it?
First letter.
I'm not sure.
Let
I
it
don't-
be H.
H better, yes. Notter proved this for finite groups, in fact over any field. And the next result is due to Maurer and Weizenberg. It is usually referred to Weizenberg. He was proved it in 1932, but in fact Maurer also have this result in 1899. It's for the group GA. In fact, both of them have the proof that it holds for any G. That for any G, the algebra of invariance is finitely generated. But both of them have a mistake in the proof. And but you can extract from the proof that for GA it holds. And then Bill, using ideas of Hilbert and Wurwitz, proved in for G which is compact Lie group, and G is complex reductive group. In fact, nowadays we have the following finite equation. Which we call no. Yes, no. Which we also call Hilbert invariant theorem. Yes, still not okay. That if G is reductive and X is affine and G is acting on X, then the algebra of invariance is finitely generated. A bit more general setting because X is not an affine space but an arbitrary affine variety. And the converse was proved by Popov. That if such an algebra is finitely generated for any X, then G is reductive. Okay, but surprisingly, there were many positive results, and at some moment Nagata gave a counterexample to this original question.
So that the result due to Popov is negative, not positive.
Yes, it follows from the counterexample that I am going to. I think that it will be better written here because it is converse to the statement, but it is in fact negative. So first negative example for the original problems. There was also some example by Ries, which was not linear, but the same year.
So Ries gave counterexample to this more general formulation.
Ries, yes. I will not write all non-linear counterexamples and examples because there are much more of them. It will be results when it's not finitely generated. So first one was Nagata. His counterexample is for the group that is isomorphic to Ga to the power 13 in Ga 32. I will also write here the example, the work of Steinberg, 1997, who was upgraded this example and written it in another way, and in particular he changed it to GA6 in GL18. He simplified Nagata's arguments. Okay, but it was much more later. Let us return to a bit earlier times. There was also example by Roberts in 1990, but it was non-linear. So I will write it like this. It was example with invariance with respect to GA. And I'm writing it because it leads to the counterexample which is linear, counterexample of a component in 1994. So you see the gap between the first example and the next example is quite a big one. And she gave an example of for GA12 inside GL90. Further, there were several examples, a series of examples of Mukai. In particular, there is an example for GA3 inside GL18 and GA4 inside GL16. And then once again, two nonlinear counterexamples of Deigel-Freudenberg and Freudenberg. Nonlinear gave rise to the linear counterexamples of tiny water. There is also a unipotent group, but non-commutative, GA7, GA in GL13, and GA18, GA inside GL27. And Freudenberg in 2007 gave an example for the smallest GL, which as far as I understand is known now for GL11.
And this nonlinear example, this GA action is also on 7-dimensional vector space, on 6 and 5-dimensional vector.
Yes, 6, 7, and 5. So, in fact, these GA, non-linear GA actions which with non-finitely generated invariant rings, it means that this the corresponding locally nilpotent derivation have non-finitely generated kernels.
No, but 7 is in Robert's case, and here,
Here
6.
and 5.
But it's strange that Freudenberg's work was, I think, the first. So maybe it was published later, but it's about 6, and Deigel from the book about
Yes.
5.
Maybe I tried to check the literature.
Earlier work about 5, and next work about 6. This is because of reference classes.
Oh, I think yes.
Okay.
And
maybe it's
do you understand what is the structure of semi-direct product? I'm trying to understand how to act GA on GA7.
So it is given by 4 triangular computing derivations and 1 triangular which semi-commutes with them. I have them written in the, but I don't think that it's a good idea to write them here. It is written in Freudenberg.
Are there examples for not important?
It's not immediate in some sense.
Yes, when you can add, it's better to have a smaller group, and if you have some, so the reductive part can be destroyed by the Hilbert invariant schema.
And what about, I don't know, GA2 action? Because
To make smaller,
to make smaller the group.
I don't know. There are some results about GA2 actions, but I haven't read about this. I don't know.
And do you know some examples about, you said that 11 is the smallest which
Seems to be known.
It just seems to be known, and other examples that, I don't know, in GL5 it's impossible to have such a group.
No, I don't know such positive results.
the central problem here is not the size of GL, but size of this unipotent group. So the best known is three-dimensional given by Mukai.
So about two-dimensional.
And two dimensions, this is a big question. Maybe this is a main question in this area. And also, short comment. Yulia produced a long list, but in fact there are only two constructions. First construction is due to Nagata and modified by Steinberg. He is not Steinberg because he is from Australia. And another construction due to Roberts. And all these further results, these are modifications of this idea.
I'm sorry, can one characterize which locally important derivations give rise to a linear action? Can we characterize?
Linear locally important derivation give rise to linear.
No, I think that the question is which examples of this kind give an example for this, yes?
No,
I don't think that there is some general characterization of such.
No, the question is another.
Another question?
You write down some locally important derivation.
Yes.
Let's say it corresponds to linear JA.
Okay.
No?
When the derivation, I think,
Is linear.
Of degree 0, yes.
What does it mean?
You have gradient and it should be of degree 0.
Okay.
Okay, the time is going, and I have about 9 points for my talk, and it was only 2. So let me try to give some proofs and some constructions in more details. First, let me say a few words about this very well-known positive result, finiteness theorem, Hilbert invariance theorem. Maybe many of you have listened about it in some courses, but I think it's worth to mention. And recall some main steps. Let I have this algebra B, and it may be proved that B is a sum of the invariant algebra and some invariant subspace which is complement to invariant algebra. It is unique, and so we have such a canonical decomposition, and we consider a Reynolds operator which is a projection from B to B to the algebra of invariance. And the idea is as follows for the case where when B is an algebra of polynomials. We take the ideal generated by invariant polynomials which have no constant terms. Since it is an ideal, it is finitely generated.
So this is how Hilbert proved his Hilbert basis theorem.
Yes.
He wanted to prove that this ideal is finitely generated, so he proves that any ideal is finitely generated.
By Hilbert basis theorem is finitely generated, and then we the goal is to prove that these guys generate the algebra of invariance as well. And this may be done by induction of a degree. So if f is some invariant which has degree n, then we can decompose it since it belongs to the ideal, and then we apply this Reynolds operator. Its main property is that it is doing like this, when you apply it to an invariant, it is
It's just a projection.
yes, it's a projection, and it's not homomorphism. So so when you apply it to the product of any element and an invariant element, we obtain this thing. It follows from this decomposition. And then this is equal to f, and this P1 PL is Reynolds operator have degree less than we are considering, less than n. And so we can use here the induction hypothesis. They can be represented as some polynomials in f1 fm, and so the whole thing is represented as a polynomial in f1 fm. Okay, next let me say a few words about positive results. For unipolling groups. Let me formulate the theorem of Hajiyev. It is as follows. Let G be a connected reductive group. B is its Borel subgroup. And U is the maximal unipotent subgroup in B.
So better to say the unipotent radical.
Yes.
This is maximal unipotent subgroup in G and unipotent radical in B.
Yes. And let Z be a G variety. Then the algebra of invariance with respect to U is finitely generated.
So for any such Z,
Yes.
corresponding algebra of invariance will be invariant. Or
Finitely
finitely
generated.
generated.
Yes. Let us use this theorem to prove the result of Maurer and Weizenberg. Let me recall the result. If G A is inside some G and K, then the algebra of invariant of a polynomial ring with respect to GA is finitely generated.
So, Mokai counterexample is for GA3. For GA1, the answer is only positive.
Oh, yes.
So the only remaining case is GA2.
Okay, everyone knows that we can realize GA as a subgroup in SL2. And the idea is as follows. We will prove lemma. That any such action can be any such action is a restriction of the representation of SL2. Let me denote it by U1. Any representation of U1 some another GL. And then if we will prove it, then lemma plus the result of Kajif gives us the Maurer-Weizenberg theorem.
So it's not clear why W should be different from B.
Why not?
So actually, so if you restrict, so the representation space will be the same.
The representation space will be the same. Because otherwise you will not obtain a proof of your theorem.
But it will be not the same, I think.
I think it will be the same.
But let us.
Okay.
So let's see.
Yes, let us prove lemma. Okay. Lemma. Okay, we have a representation rho from U1 to GL. Let's consider its differential, and I'm interested in the image of this matrix. It is some matrix in the endomorphism group of GL, and it is nilpotent. Because this thing is nilpotent, because this thing is unipotent. And what we have to do, question, is to find for any such a nilpotent matrix a representation of SL2 such that the matrix goes to the same A. If we will find it, then we will have the equality that differentials d rho is the same as d rho tilde, and if differentials are equal, then the representations are equal as well, because we have a connected group. Since this one is one-dimensional, it's enough to prove for one matrix. Okay, so the question is why there exists such rho, that the image of this thing is any given nilpotent algebra A. Matrix A. Yes, and we know that there is a Jordan normal form. So the matrix A can be written as, in some basis, as a Jordan normal form with cells of size I1 and so on. Yes, it will be the same. A, I don't know, R. And let us take by this V the representation of SL2 the following. Where this Ri is a standard SL2 representation, which is reducible of dimension A1, so the binary forms of degree I.
Can we say that we consider the transpose matrix for the other generating of SL2
No.
algebra?
No, there will be some fractions. For the SL2 triple consists of H, E, and and F. So this F, this will be not a standard Chardon law.
Why not?
Just do computations.
So these things, it corresponds to y to this operator on Ri, and if I will take
So you
If I
are
will
trying to
start
say
with
that
X.
there are some coefficients, yes?
yes, there are some coefficients, but if I will take x to the power n and then apply this many times, then I will obtain all basis vectors, and this will be
Okay.
chain
The
of
opposite
vectors.
is something like x multiplied by del y.
Yes, I don't know why the opposite doesn't work.
Okay. Yes. So there are some coefficients, but
Yes, there are some coefficients, but we can add them to the basis vectors. I think.
So you see the space is the same.
Yes, the space is the same, so I changed here to V because the dimension is the same here. Because this it should work. And I added it here.
So this is a very strange lemma. Any representation of one-dimensional unipotent group comes as a restriction from SL2 representation. Unbelievable but true.
Any important matrix participates in this S2.
Any unipotent matrix can be included into SL2 triple.
Okay, there are positive results, but the math is not very positive, so we are going to more interesting counterexample parts.
And also Yulia didn't prove Hadjiev's theorem, but if you know the theorem of representation with highest weight, this is very easy. This is more or less automatically follows from complete irreducibility of representations.
So about Nagata example, I would like to say more about Steinberg example, not about Nagata, because Steinberg modified his proof and it is more easy to listen, but I will tell a few words about the ideas that Nagata has. The idea is that for any M, doesn't exist a curve of degree for n such that multiplicities are at least m at each of 16 points in projective plane, general points. So he considered a surface X that is obtained from P2, from the projective plane, by blowing up in 16 general points. And in fact, we have to consider the Cox ring of this X, and this Cox ring is sometimes not finitely generated. So one can construct such an action of some unipotent group U. I will not say many details. On the space of dimension 2R, where U is some subgroup inside GAR, such that they are isomorphic as graded algebras, and this will be not finitely generated.
So that the paper due to Cox is in 1995, and I believe that there was not a concept of Cox
Yes.
ring.
Clearly, Nagata didn't say Cox ring, but essentially, if you look, he constructed exactly Cox ring.
So yes, it was the risky idea to consider the
Ring of sections. He called it ring of sections.
yes, such that V is
And this is completely genius work. So it was very original. Nobody expected that it's possible to construct. And when Nagata discovered it in 58, he was proposed to give a talk at the International Congress of Mathematics in 59. And so he somehow announced his result for the first time at the International Congress.
Let me mention here the result of Mukai, which is much more later, that the blow up of Pm in R general points has finitely generated Cox ring if and only if such an inequality holds. And sometimes this doesn't hold, and it is finitely generated, not finitely generated. Okay. Now let me continue with the modification of Nagata's example, Steinberg counterexample. Let me first formulate a construction. I follow here the brochure of Ivan Vladimirovich. Maybe there are some more so it will be very, how to say, I don't know English, so I will not say. Let us consider 9 points, and they will be distinct, and the sum of all of them is 0, not 0. And now I will consider the subgroup of GA9. It will be the active group. It consists of such tuples that 3 equalities holds. Their sum is equal to 0. The first equation. The second equation is that A1C1 plus A9C9 is equal to 0. And the third equation is these cubes of this A equal to 0. So 3 equations in GA9, and one can see that it is isomorphic to GA6. They are independent since you can find a determinant 3 by 3, and after changing, after renumbering, it will be non-zero using these conditions. Let us denote in our algebra B variables in the following way: x1, y1, x2, y2, and so on, x9, y9. And we will act here also by torus of dimension 8, with this condition. So we have the 8-dimensional torus and the 6-dimensional unimportant part. And their product we will represent it in GL18 in the following way. force acts on variables as usual. T1 acts on x1, x and y1. And the unipotent part is acting only on y's. So we have such block matches. It is 18 by 18. And still, Steinberg. That the algebra of invariance of B with respect to H is not finitely generated.
So you ask for non-unipotent groups. This is a non-unipotent group. But for unipotent part, it's also not finitely generated.
Yes, corollary. BG is not finitely generated. Why it is true? Because the proof of corollary, if you consider BH, it is BG T. Invariance with respect to G and then to T. And T is reductive. So if we assume that this is finitely generated, then we will obtain that this whole thing is finitely generated, but a contradiction because it is not finitely generated.
What is the use of this term?
It's simpler to prove that the algebra of invariant of H is not finitely generated.
It will be less, but you will obtain more D.
So he proves directly that the algebra of invariance with respect to H is not finitely generated.
So let me try to outline the proof. First, we are going to find this algebra of invariance. Let us denote some necessary polynomials inside B. One is the product of all y's. Another one is the sum of such polynomials. Y is divisible by y1. Let me denote it wy. The next one is the sum of these, the same guys with coefficients ay, and the third one is the sum with coefficients ai cubed. And one can check by direct computations that they are invariant.
So what is capital Y?
Capital Y is the product of all y's. We know how our group acts on any variables. X, y is multiplied by ty, and y is multiplied by ty, and then we add some x1. So we can check that they're invariant. It's easy. The next thing is that the algebra of invariant is the intersection of B with I missed the 3. So any invariant can be represented as yes, it can be represented as such a Laurent monomial in these polynomials if it lies in.
So it shows that after localization, the algebra of invariant is finitely generated.
Yes. The proof is as follows. Let us localize it in 1. We know that it is x1, x2, x3, x4, x9, y's, and then y minus 1. And then we can change this x1, x2, x3 by w, because w is x1, w1 is x1, multiplied by some y's. And then we can use this linear change of variables and replace this by z1, z2, z3. Because of these conditions and because this is after numbering variables. And then we try to find invariance. Let us act on this all variables, these 9, 8, 10, with the element of the form 4 elements and then all zeros. It exists for any C4, there exists such C1, C2, C3, goes by these equations. And if we will do it, then we will see that all variables are stable except of x4. So we cannot use x4 when we are looking for invariance. And in the same way, we see that we cannot use all these things. So it is inside z1, z2, z3, y1, y9, y minus 1. I'm missing some calculations, but you can check it. And then you can act by a torus. And if you act by a torus, you will see that you cannot use these guys as well. So you obtain what we needed. The third step is that they are linearly independent. Sorry, algebraically independent. Well, you can just, using these calculations, you can see that Z1, Z2, and Z3 are algebraically independent over the field which consists of all y's. They have one x inside, 3 different x1, x2, and x3, and they are algebraically independent over this, and it follows that they are algebraically independent here. Step number 4 is more exact about the invariant rings. So any element here, we already have proved that it is here, but in fact it can be represented as a sum of some homogeneous polynomials in z1, z2, z3 divided by some power of y, maybe negative. And moreover, this is divisible. So if you will divide this by this, then it belongs to B. It is also not difficult to prove. You have to compare some degrees and see that the degree of the fraction and fg determines the degree of fg, and then it should be divisible because all homogeneous parts of an element from B also belong to B. Okay, the next, I think, is the crucial step here. It is the idea with multiplicities, that the polynomial homogeneous f, commas, yes, I know commas, is divisible by y to the power m, that it has degree b, that it have. If and only if it's homogenization. Everyone knows what is homogenization, but I will write. Even with colors. Has zeros of multiplicities at least m. At these points, at which points? I have right before. At 9 points, which which are connected with our coefficients. So how to prove it? We consider one point, for example, a1 cubed. And then we are interested in multiplicities at this point, so we will move it to 0, 0 by some linear change. That's by linear. It looks like it is will not change z1. This is z2 minus something, and the 3 is. So we are moving it, and we are interested in degrees of y1. So it appears that there are something plus y1, and these two guys both are divisible by y1, and here where I write dots, it is something that not depends on y1. And then we will try to understand about this homogeneous thing, how much y1s it will have, what is the multiplicity. So we substitute this change of variables, and it appears that this f hat has multiplicities at least m at our point, if and only if f has the form y1 to the power m dot something that doesn't depend on y1. And you should check that this thing is non-zero. It follows from our conditions on coefficients. And if you have such things, then you can apply it not only to y1, but also to y2, and so on to y9, and prove number 5. So then you have to compare some dimensions and prove number 6 and 7. If number 6 is that it's something about polynomials in two variables. All polynomials in two variables of degree at most 3m, which have multiplicities at least m at any point ai cubed. It is only one such polynomial. And it looks like this. It's an easy exercise. You do it by induction.
X cubed minus y.
Maybe x cubed minus, yes, y minus x cubed. You can prove it, for example, by induction on n. You have to prove that it is divisible by one such thing and apply the induction hypothesis. Okay, and comparing some dimensions, you can find that there exists a polynomial of the next degree, of degree 3m plus 1, such that it is not divisible by y minus x cubed, and also has multiplicities at least m at each of our 9 points. And let me prove the theorem. Assume the converse. Let the algebra of invariance is finitely generated. Then you can represent it by some generators. Generators all have such a form. You can take only summons homogeneous from here, and you can also add some element that always belongs to this invariant. It is homogenization of the 3 minus the 2 cubed. And also some other things, where each such thing is some fg by some power of 1. There are some generators, finite. And we can assume that this is not divisible by the simplest one. Otherwise, you can move it to the first one. And we can assume that they all are homogeneous of degrees, of some degrees. Let me denote them by dg. From this lemma, number 6, it follows that all dj are more than 3mj. And let us fix some number m that is more than maximum. And now I'm writing an element that will not belong to the to this part, to the right part of my to this thing. Let us take f also of the same form, because it is from invariance, where f is taken from number 7 of degree a bit more, but not divisible, but with multiplicity, so it's with multiplicities, so it works. It lies inside the polynomial algebra. And it is multiplied by z1. Okay, so aim is to show that it doesn't belong to, and this will be a contradiction. We will find some element that doesn't lie here, and so it is not finally generated. Okay, assume the converse. Let it is represented in as some polynomial of these things. Let it equals to some polynomial in all these things from star. This polynomial, the result shouldn't be divisible by the first thing, because we have chosen such f that is not divisible by y minus x cubed. So it has a monomial depending only on the last guys of this form. And now we are going to compare degrees of variables on the left-hand side and on the right-hand side. We have already proved that these variables are algebraically independent. So you can consider this equality as the equality of Laurent polynomials in these variables. Okay, so we have f, z1, z2, z3 divided by, and it has some monomial p1, a1, er, er. First, let us look at degrees in z1, z2, z3. Here, it is equal to 3m plus 1. And on the right hand side, it is sum d1, e1 plus dr, er, because of our notations. And then we consider degrees in 1. So it is z2 grading, in fact, yes. On this side, it is of this form. And on the left side, it is 3m. Oh, sorry, m. It is m here. And now we can subtract it. This coefficient 3. And we will see that 1 is equal to d1 minus 3m1. But we have already noticed that these coefficients all are positive. And we have to obtain 1. So from these assumptions on degrees follows that this thing is one-dimensional, and but there exists such a polynomial, and it plays a role here. And it follows that only one of e has to be equal to 0. And all others are equal to 0. But this is a contradiction, because if we will look here, then we will see that m is equal to mg, but m was chosen as a number that is more than the maximum of all of them. So this is the end of the proof. Let me say once again that I think the crucial thing is number 5, that this summand belongs to B if and only if we have some condition on multiplicities of 0. And this condition on multiplicities, it holds only for one up to scaling polynomial of degree 3m. And for some polynomial that is not divisible on this y minus a cubed for degree 1 more. And then we can obtain a contradiction using this Z2 grading.
In fact, what you prove. So what is the reason why this algebra is not finitely generated? Just because if a finitely generated algebra is graded by something, then we can take homogeneous generators, and their degrees will generate the semigroup of grading semigroup.
Yes.
And this algebra turns out to be graded by non-finitely generated semigroup. This is what you explained. And so it's not finitely generated.
Yes.
Certainly, this looks rather technical, and it's indeed in some sense technical. But Steinberg proof is completely elementary. It can be explained to those who know linear algebra and nothing else. What is a matrix? What is the action of matrix on vectors? Certainly, Nagata used some algebraic geometric arguments, some curves, some order of 0 poles, and here are only polynomial fractions at matrices, nothing else. But he just developed, just to imitate Nagata's idea.
Okay, the next topic is about Roberts and Kuroda counterexamples. but I would like to mention it to come to the components counterexample. The example of Roberts is as follows. Let us consider the algebra B, as usual, of polynomials, but let me denote these variables in the following way: x, y, z, s, t, u, b. And then let us consider the derivation dt, where t is at least 2. It looks as follows: x to the power t plus y plus zt plus x, y, z. Here are all t plus 1, sorry, and here t. So, and the result is that the kernel of this locally important derivation is not finitely generated. It is the ring of invariance with respect to nonlinear GH.
Is t a parameter?
T, yes, it is a parameter.
So this holds for any t.
For any t at least 2. Let me also mention here the result of Kuroda, which is so it looks like a very special thing, but Kuroda proves that it holds for many locally important derivations.
But when there is no b there,
Hmm?
there is no b,
B is a polynomial. B.
maybe the last
The last one is V, thank you. Okay, let us take a matrix of some integers of size 4 by 3. And we will consider such integer numbers that the diagonal element is more than all elements in the same column. And also we have some condition, some inequality. They have to be at const 1, where mg is a minimum inside the column, but on the first 3 rows. So it is some condition on integer numbers, and for example, it appears that if all these items are at most 10, then there exist at least 2 million matrices that satisfy this condition. Let us take a locally important derivation d, also on 7 variables, but I will denote for convenience as x1, x3, y1, y4. It takes all xy's to zeros, and ay goes to some monomial in xy and x2, x3 with these integers from the matrix. And indices are y here. Okay, then the kernel of this derivation is not finitely generated. In particular, we can take the following matrix to obtain the so-called generalized Roberts R, 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 S, 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 and all zeros, where R is between S and 3S divided by 2. Then we will obtain the derivation that we have already seen several years ago on the talk at our seminar given by Veronika Trumova. It has not finite generated kernel if and only if such conditions hold. X, Y, Z to the power S. Okay. And now I'm going to show how a companion obtained the linear counterexample using these non-linear ones. Okay.
What is this matrix?
It is this one. For by phi matrix, one can check that these two conditions are equivalent to this for this matrix. Let me write a construction. We have to take GA12, and it is inside GL19. It will look like this. Where M can be written explicitly. I will write it, but maybe it will not help, but it is more pleasant to have so it is some matrix filled with T1, T2, and so on to T12. And all other entries are equal to 0. So we know exactly how it acts on any vector from the vector space 9 dimension. Okay, and the theorem is that the ring of invariance is not finitely generated. Let me try to give a proof. First, I will denote by Q the algebra, the polynomial algebra in 4 variables, W, X, Y, Z. And companion uses several times the following lemma. Let theta be a locally important derivation of such a form. So I have extra lambda and mu. They go to Q and Q goes to 0. Then it's easy to find its kernel. The kernel of theta is generated by some evident element from the kernel. And now we applied it several times to 11 locally important relations. So we can consider B the polynomial algebra in all 90 variables. I will denote 19 variables. I will divide them into groups as TUV. Q will know that it is these 4 variables. Also, there are 3 variables S, 3 variables T, 3 variables U, and 6 variables D. And now we consider, I will not write all 11 derivations, but let me write one of them. Something like this. It is of this form as in lemma. And what we are going to do? We are going to find invariant ring. And this invariant ring, it is the invariant ring with respect to the first derivation, with the second derivation, and so on, with all the derivations. And we can compute it. For some easy locally important derivations, we delete v5 and v6 and take some v5 prime, not prime, but I forgot how to say it. Prime, yes. And then consider the next one, delete these two, add some v4 prime, and so delete, 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 and obtain here one variable v. Then we have some extra derivations, and they only one variable uu is remained in this invariant ring. Here also we obtain some one variable t in the invariant ring, here s, and finally, after applying all this invariant with respect to 11, not 12, but 11 of them, we obtain the ring in w, x, y, z, and here 4 more derivations. And if you will write it, then you will see that this derivation is the derivation d2 from Robert's example, with only one another thing, that there's also some extra variable which just goes to 0. So the ring of invariance in the example of Campanile is the same as the ring of invariance in the example of Roberts. With some extra variable. But if this one is not finitely generated, then the whole one is also not finitely generated. Such a plan. Okay. Can I take a few more minutes to say a word about, so I have the last point about observable subgroups.
Okay, so I propose to give you extra minutes because this is about Popov's theorem, right?
Popov's theorem, not. I can also say about Popov's theorem.
Maybe extra 10 minutes.
No, it's too much. I don't have so many material.
Minimum 10 minutes.
Minimum 10 minutes.
Dance, think, but minimum 10 minutes.
Okay. Well, the last point is about deleting these conditions about GLM. So, why we are considering GLM? No one knows. Let us change it to any reductive group. And let this group act on some vector space. Recall that the group G is called observable if and only if its definition, the homogeneous space is quasi-affine. It is affine when G is reductive and quasi-affine when G is, so the term is called observable. when we study invariant theory, it's enough to consider only observable groups, because you can change any group by its observable whole. By intersecting all observable subgroups that contain G. And if you will take it, then the invariant ring will be the same. So if you are interested in invariance, you can think that your group is observable. Theorem of Grossman's. Let G in some reductive subgroup, I don't know how, in our reductive group is observable. Then the following conditions are included. First, for any both G module V, the algebra of invariance is finitely generated. The condition we are interested in, yes? And the second condition is that the algebra of regular functions of a homogeneous ring is finitely generated. Note that it doesn't depend on V. So the first condition, in fact, doesn't depend on V, only on both G and G. And there is also the third condition, that there exists a fine embedding of this homogeneous ring inside X.
Homogeneous space.
So homogeneous space inside X, such that the codimension of boundary is at least 2. And in such a good case, if this G module, if any G module is finitely generated, we call a subgroup Grossman's subgroup. So the original Hilbert's problem is about describing Grossman's subgroup in GLN. But we can also try to describe Grossman's subgroups not only in GLN and in any reductive group. Let me formulate a positive result, which generalizes G theorem. If you consider a unipotent radical of any parabolic subgroup, then its ring of invariance, the algebra of invariance, is finitely generated, so it is a Grossman's subgroup. And by Popov and Pommering, it was conjectured in which cases it is finitely generated, in which cases it is Grossman's. Let us call the algebra, let us call the subgroup of G regular. If the group G is normalized by the maximal torus in both G.
We have Meaning.
Sorry. Only one moment. Any observable regular subgroup is Grosshan's.
What does it mean, regular?
It means that it is normalized by
sorry.
the maximum source. That's all what I was going to say. Maybe I can say something more if you ask me something.
So you didn't plan to prove Popov's theorem?
I can say a few words about proving Popov's theorem if it's a good idea.
This conjecture is open. In recent years, during the last 5 years, there were several proof announced, even once published. But the common opinion is it is not proof, so these proofs are not clear.
Actually, I can find this paper. It's some paper of Popov Pomeranian. Yes, where it's was conjecture, or it's some. I can find this.
It was independent conjecture.
By two different papers.
Yes.
I don't know where is the original formulation of this problem, but now there were several preprinted publications where this conjecture was proved. But it seems that it's not the case.
So, what we know from the existence of Nagata counterexample, that there exists some unipotent group in some GLN such that the algebra of invariant is not finitely generated. Okay, let us for this group consider the row. Maybe it is something. It has. Consider such unipotent subgroups that are normal divisors here, and all of them are unipotent. Yes. Such that ni plus 1 divided by n1 is one dimension.
For unipotent groups, there always exists such a chain of normal subgroups.
Yes. Now let us consider the rings of invariance of these subgroups. They will be included in other direction. And we know that the last one is not finitely generated. And the first one is finitely generated.
First one is a polynomial.
Yes, because it's equal to. This means that at some point we can let us write the ring of invariance with respect to ni as the ring of invariance ni plus 1 as the ring of invariance of ni with respect to the factor, the quotient. So at some moment we have a moment when the inner thing is not finitely generated and the outer thing is finitely generated. No.
Conversely.
Conversely, yes. That this thing is not finitely generated and this thing is finitely generated. Okay, and this is one-dimensional unipotent subgroup. Okay, and then we can construct such an action on B that what I'm proving here. Do you understand? We have to prove the converse, yes? So we have to construct for any non-reductive group, we have to construct, let H be non-reductive group. So it has some unipotent radical. And I'm going to construct such action that this one is not finitely generated.
Where B is not necessarily polynomial algebra.
Yes, yes, it's some A. First, let us construct such that this thing is not finitely generated. Okay, and we do it using this quantity. We know that there is a Nagata. There exists some homomorphism from non-trivial unipotent group to GA.
Admits a surjective homomorphism to one dimension.
Surjective is homomorphism, and then we can consider the following action. Let me denote it by A. Where we take for A this finitely generated thing. It is some affine algebra, V and I. And this is not affine. And the ring of invariance for this action for HU will be the same as here for GA. So it was with respect to HU, and then we have to take some action of H, not of HU. And Popov considers the action on the direct product. So let our H has a Levy subgroup S, and let us consider the action on their direct product, natural, and then you will obtain that for this Z, the ring of invariance with respect to HU is the same as the ring of invariance on this yes.
H.
So you should take
one
not
moment.
HU.
Yes, like this. And H is acting here.
And that is the spectrum of A.
Yes, okay.
So this is a rather straightforward construction. Knowing that there exists at least one action of a unipotent group with non-finitely generated algebra, you construct this for one-dimensional unipotent group, then for any unipotent group, and then for any non-reductive group.
So the problem here is that this action is super non-effective. Well, in case of unipotent group, it's just really acts only one dimensional
Yes.
group. Yes. And how to construct effective action? If someone knows, it will be interesting.
Maybe also some construction.
Just add the variety of the same group and act on left translations and multiply these two. And you obtain
It's
effective.
not obvious why.
You consider just effective action on another variety and multiply these two.
You have some
It
kernel
seems that
of
it
non-efficiency, and by just acting by
You need to check that there is any ring of invariance with this.
Okay, so thank you, Yulia, very much. Maybe some questions.
I have a question. You take the example of Mukai of dimension 3, J is about 3.
Yes.
Is it written somewhere as explicit matrix with 3 parameters?
I haven't seen, I think we should check. But I think that I haven't seen.
Maybe in our books on Cox rings something is written. But in fact, this Mokai paper, this is a preprint, not published, 3 pages long. So it's not easy to understand what is written there, but I remember that we tried to write down something in our books.
Because you can write it down. Like example.
Like example of algebra.
Yes.
Maybe, I don't remember. Yeah, I remember that we tried. But did we write or not? I just don't remember. Okay, any more questions?
So, am I correct that if we act by GA on the vector space, the algebra of regular functions is always finitely
Yes,
generated?
it's Maurer-Weizenburg theorem.
Yeah, but for
It's linear action.
yes, yes, but for an affine variety, if we have an action of okay,
It's
Yeah,
difficult to
okay,
say
okay.
what does it mean linear.
Right, yes, okay, understand.
But even for affine spaces, there are non-linear action of GA with not finitely generated.
That correspond to non-finitely generated kernels of local invariant distributions.
Because there are GA actions on affine varieties.
Yes, that are not linear.
Okay, it's
It's like all these derivations that I have written here, dd and so on. They have not finitely generated kernels, and they correspond to.
okay.
And it's known that for any action on an affine variety, you can embed this affine variety to a affine space
Yes,
such that
such the actions
the
linear.
action should be linear.
Mhm.
So if you have J actions with not finitely generated invariants, then you embed, and all the invariants are finitely generated, but embedded or invariants of this subalgebra is not finite.
Yes, so in a finitely generated algebra, maybe not finitely generated subalgebra is what we are trying to do here, because this one is finitely generated, but we are looking for some subalgebras that are not finitely generated.
And also I remember when I was a student, I came to Wilbur-Konishik seminar, and this theorem of Groska's was at that time 20 years old, but it seems it was our opinion that this is very useful. We have discussed it many times, we gave talks, because look at this condition number 3. It's very effective. You take G mod H, and you are looking for a affine embedding of this quasi-affine homogeneous space with small boundary, such that the complement to the open orbit contains no divisors. So very effective condition, and this is a way to prove results for Hilbert's 14th problem. And it was a feeling that we can take, say, some G, reductive GLN, some unipotent subgroup, and construct such embedding. And there were many attempts. I tried by myself several times. I have some related publications, but no essential results. So this, at the first glance, a very useful condition. It's not so productive.
So these embeddings, they are very difficult in these examples.
To construct such example. Secondly, if you know the condition 2, if the algebra of regular functions on this G mod G's, then take x, write down x equal near 2, x equal spectrum of the algebra of regular functions on G mod G. And one can prove that this is the embedding with small boundary. So the complement to the open orbit contains no divisor. And this is the only normal embedding with small boundary. But to construct it, you should know item 2, that this is finitely generated. And if you don't know, just construct by hand some points whose stabilizer is this G small and such that the closure of the orbit doesn't contain divisor in the complement. Doesn't work. So many times Groskans wrote a book and there are some results, but no serious success, no serious achievements in Hilbert's work. Okay. So now it's 20 minutes more. So many thanks to Yulia.
Sorry for doing.
And next talk will be in almost 1 month. It's by Sergei Gaifurin. So he has 1 month for preparation. We will continue on May 20. Now we stop clapping. Yes. It was a new
Previous two talks we left.
Okay, let's so brilliant.
We will stop next time.
We will stop next time. Next talk. We will continue.